Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Farhan Hidayah binti M. Pajar. I am a master's student in University Technology Malaysia UTM campus in JB. Today's video will be a presentation for 2020 IEEE International Conference on System Engineering and Technology. The title for this paper is Semi-Global Leader-Follower Consensus of Linear Multi-Agent System via Time-Varying Gain. The author for the paper is myself, Dr. Nurul Adila Muhammad Subha, my supervisor, Prof. Rosaria Abdul Rahim, my co-supervisor, Dr. Fazila Hassan, and Nur Ikhwan Hamzah. Cooperative control is a control system that enables agents to obtain information from each other as long as there is communication channel and they can communicate between each agent. In consensus, cooperative control can also be categorized as a leader-follower topology, where there is one leader in a topology. The agents work together based on the leader's information. In consensus, the cooperative control is divided into two categories. Firstly, the cooperative leader control, which is the leader would have access to its followers' information, and the non-cooperative leader control, when the leader does not receive any information regarding its followers. It can only give information to the followers. Now, what is the difference between cooperative and non-cooperative? Cooperative leader control is more robust to disturbance. However, non-cooperative leader control has a faster response towards communication between agents. This is an example of a cooperative leader control, where it is represented by the green line, or just a solid line between the leader, which is marked by the number 0, and agents 1 and 4. Agent 1 and 4 will receive information from the leader, and the leader can receive information from the agents itself. Now, in the next example is the non-cooperative leader control, where it's presented by the blue arrow. The leader 0 can will only transmit information to the agents 1 and 4. However, the leader 0 will not be receiving any information regarding agents 1 and 4. This is also known as non-cooperative leader control. The follower agents can be connected in graph topology, and this is divided also into two. Firstly, directed follower graph and undirected follower graph. Directed follower graph is a graph where the follower only has one-way communication with its neighbor. For example, agent 1 can transmit to agent 2, but agent 2 will not be able to transmit to agent 1, or agent 1 can only give information to agent 2. However, agent 1 does not receive any information regarding agent 2. Undirected follower graph is where the agents or the follower has access to the neighbor's information, whereby each agent can receive and transmit information with each other. In this paper, we focus on undirected follower graph. Why undirected follower graph connections is because, firstly, for the future implementation, it is used widely for fault detections and reassign team goal. The consensus problem with input saturation has a general solution, which is mainly uses low gain, or a combination between low gain and other methods, such as low gain high gain, or low gain Riccati, or low gain Lyapunov. And the example I'm showing you right now is a paper written by Chu Hongjun, where his method to solve consensus with input saturation problem is by using low gain integrated with Lyapunov. The leader control topology is a non-cooperative leader, as shown in the graph below, where leader 0 will transmit information and the information will only be received by agent number 1 and by agent number 4. Agent number 2 and 3 does not have direct connection to the leader. The follower topology, however, in his paper is written as directed, as shown in the graph below. The problem statement for the written study is firstly, the common solution used for consensus problem, as I mentioned just now, is with input saturation constraints, utilizes mostly low gain feedback control approach. However, it is said that if using only low gain feedback, the gain feedback will be redundant as the value approaches near 0. Second, limited work has been done on the effects of weighted coupling gain approach in consensus problem with saturation effect. Then, thirdly, weighted gain involves only subtraction and will lead to a simpler calculation, thus avoid complicating the controller, which can also be used online. Now, the objectives of the paper is firstly to design a consensus protocol with weighted time varying gain to improve convergence performance, and secondly, to observe the performance of network multi-agent with cooperative and non-cooperative leader by utilizing the time varying weighted gain. So the study in this paper will focus on both the cooperative and non-cooperative leader control connection. Moving on to methodology. Analysis. Firstly, the analysis of the previous algorithm is done. The simulation for the algorithms studied in the analysis of the previous algorithm is studied, and thus a leader-follower consensus is constructed, as shown in here. Xi marks the agent number, and XL is the leader, whereby Xi has feedback and XL does not. Saturation is then constructed by using the following mathematical equations. Only then, after this is done, will we implement coupling gain feedback method. The simulation comparison with benchmarking method is done. We complete the simulation comparison with benchmarking method by convergence test, which is divided into two, whereby we test it on cooperative leader and non-cooperative leader control connection. This is the mathematical difference in the algorithm proposed in the referenced paper, which is written by Chu Hongjun, and the proposed algorithm. Chu Hongjun represents their gain feedback or the low gain feedback by C, and it's implemented in front here, while ours we represent by weighted gain, which is represented by mu ij, and is implemented here in the equation. Performance of coupling gain algorithm is measured in two ways. Firstly, the cooperative leader. Secondly, is the non-cooperative leader, whereby the cooperative leader is represented by XL plus matrix A XL plus matrix B and the saturation. Matrix B saturation UL is the feedback loop into the leader's algorithm. The non-cooperative leader is represented by only XL plus matrix A of XL. There will be no feedback going into there will be no feedback from the agent going into the leader. On the figure beside, it shows the connection where the green arrow shows the non-cooperative connection control, and the dotted solid line is representing the cooperative leader control. This is the effects of parameters on cooperative leader topology under influence of the proposed gain. These effects is based on the value of epsilon from the equations before. The first graph of this slide shows the value that shows the value of epsilon, which is set to 0.1, while the second graph is when the epsilon is set to the second graph is when the epsilon value is set to 1. The third graph is when the epsilon value is set to 10, and the fourth graph here is when the epsilon value is set to 20. As you can see, the most also from here you can see that the third graph, which is epsilon value is set to 10, is the fastest response when epsilon is set to 10. Therefore, it is observed that from the consensus, the convergence time is decreased by increasing the value of epsilon, regardless of the type of the leader, either cooperative or non-cooperative. However, when epsilon is set to 10, it is found that this is the best value for the particular topology with the lowest convergence time. This is the result of comparison between the proposed topology and the topology used in the benchmark paper. The left side is the proposed topology, and the right side is the proposed benchmarking paper by Chu. As you can see here, the left side reaches consensus at about less than 150 seconds, while the right side does not reach consensus. The convergence time for the consensus algorithm proposed in this paper compared in the previous slides shows that the proposed algorithm can be seen that the proposed time varying gain formula yields a stabilized result. However, the compared paper does not reach consensus. This justifies that the proposed algorithm can be adopted to solve the consensus convergence problem for this topology with a cooperative leader connection. The second result shown here is the comparison between the non-cooperative leader topology of the proposed algorithm on the left, and on the right is the non-cooperative leader topology of the benchmarked paper. As you can see on the left, it reaches consensus also less than 145 seconds, while on the right it does not reach consensus. It is observed that in the previous results that for cooperative leader connection, the proposed algorithm is able to reach consensus, while the benchmark paper is not able to reach consensus. As a conclusion, this study is conducted to analyze and suggest an improvement for the network multi-agent system with saturation constraints in an undirected topology with both cooperative and non-cooperative leader. The proposed weighted gain algorithm is compared with algorithm in Chu Hongjung's work, which uses low gain feedback, and it could be seen that the proposed algorithm can be adapted to the topology given. And thirdly, the proposed algorithm is able to produce a better performance for undirected topology with both cooperative and non-cooperative leader. This is the reference for the presentations, and thank you.